Students, in this class we will learn about the nth root of a complex number. Now the question is, why do we need this nth root of a complex number? Now imagine you have something like this: x to the power 4 is equal to 16, and you are asked to find the value of x. So what would you do? You would move this power, which is 4, it's actually the exponent of x, and when you move this to the right, this power would become as 1 over 4. Okay, so it would become the reciprocal of 4. So what do we call this? We call this as the fourth root of x. And how do we write this quantity? So you know that I can write 16 as 2 raised to the power 4, and that has to be raised to the power 1 over 4, and that would give me 2. So x is equal to 2. So what is the understanding? The fourth root of x is 2. So that is the meaning. But in this case we are actually dealing with only numbers which are easy to handle. Now the question comes, what if instead of x be the number that is being given to us, if we are given some complex number z, how are we going to find the nth root? Now when we say nth root, the value of n can be 3, the value of n can be 4, 5, it can go on. Okay, so that is what we are trying to understand. So we would start out like this: let z be a complex number, any complex number, okay, and let omega be the nth root of z. So we would write this, so this would mean that omega raised to the power n would be equal to z, and it can also be rewritten as omega is equal to z raised to the power 1 over n. So that is the understanding we have here. Now since both of these are complex numbers, I'm going to take, let z be equal to r times cos theta positive I times sine theta, and omega be equal to some rho of cos phi positive I times sine phi. So from 1 I can rewrite this as rho of cos phi positive I times sine phi, and that has to be raised to the power n. So this is going to be the form which is equal to r times of cos theta positive I times sine theta. Okay, so we have got equation. Now by the Morris theorem, we know that WKT stands for, we know that I can rewrite this as rho to the power n of n times phi positive I times sine n phi. Okay, now this is equal to r times, now cos theta positive I times sine theta. Now this can be written as cos of some theta positive 2 times k pi positive I times sine of theta positive. This is the form we need to, this will generate all complex numbers. Now equating both sides, we would get, so what would we get? First we would equate the magnitude, right? So this means r to the power, rho to the power n is equal to r. So from here rho is equal to r raised to the power 1 over n. So this is what we've got when we equate the modulus. Now equating the argument, that is n phi is equal to theta positive 2k pi. So we already have this equation, which is n times phi is equal to theta positive 2k pi. So from here I can write phi to be equal to theta positive 2k pi divided by n. Also I've got rho to be equal to r raised to the power 1 over n. Now if you remember, we started by taking omega raised to the power n equal to z, and then omega to be equal to z power 1 over n, and then I said that omega is the nth root of z. Okay, so if I were to club every information that we have got, so therefore z raised to the power 1 over n is equal to omega, but we know that omega has been found to be rho. In other words, omega was taken as rho times of cos phi positive I times of sin phi, and we know that rho is r raised to the power 1 over n, so that's going to be r raised to the power 1 over n of cos, but phi is theta positive 2k pi divided by n positive I times sine of theta positive 2k pi divided by n. So on the left we have got z raised to the power 1 over n. So this is the nth root of the complex numbers. One important point when we are dealing with the nth root of the complex number, now k can take any values. Okay, so that means there are infinite number of values, infinite number, okay, of values possible in this case, but distinct values of obtained. Okay, distinct values are obtained only for k being 0, 1, 2, 3 and up until n minus 1. Now after that the values will repeat. The nth root of the complex number will repeat, okay, itself when k takes the value n positive 1, n positive 2, etc. Okay, so the values are unique only for these values of k, so have that in mind. So that is very important. So to conclude, now I have written here as k times of 2 pi, now just to show you that the values of k are varying. So finally the nth root of the complex number is given as z raised to the power 1 over n, or you can write simply as omega equal to r raised to the power 1 over n of cos of theta positive 2k pi divided by n positive I times sine of theta positive 2k pi divided by n. Okay, where the values of k are 0, 1, 2, 3 upward to n minus 1. So this will be the final solution.